chemical bonding. We have studied about an atom and its structure in detail, isn't it? Also, we know that the different type of molecules and compounds, which are made by the chemical combination of atoms. Here he comes. Element number 8, atomic mass 16. Oxygen.
1, 2, 3.
Oh. He makes friend with iron.
Ah.
It's unfortunate to place he so long. Oxygen recovered quickly and now he play with barium. Oh. Be careful. If so, have you ever thought why atoms combine together? Do atoms of all the elements combine in this manner? Let's examine. Before discussing about this, we should understand what is electronic configuration and stability of atoms. We all know that an atom consists of the central part, called nucleus, which contains positively charged proton, and electrically neutral, neutrons. The number of protons in an atom is called the atomic number, and is represented by Z, while the sum of protons and neutrons is called its mass number, A. Besides protons and neutrons, there are negatively charged particles, called the electrons, which revolve around the nucleus in various shells, or orbits. This arrangement of electrons around the nucleus of an atom, in various orbits is called electronic configuration. Please note that the number of electrons in an atom is always equal to the number of protons. This makes an atom electrically neutral. Every orbit has a certain capacity to accommodate electrons. The maximum number of electrons that can be accommodated in a particular orbit is determined by the formula 2n², where n denotes the orbit number. The first orbit, n, equals 1. Therefore, 2n² equals 2. Hence, the maximum number of electrons that can be accommodated in the first orbit is 2. Similarly, the second orbit, n, equals 2. 2n² equals 8. Hence, the maximum number of electrons that can be accommodated in the second orbit is 8, and so on. But remember, the outermost shell could only accommodate a maximum of 8 electrons in an atom. Let us see an example. The atomic number of potassium, K, is 19. Therefore, there are 19 electrons revolve around the potassium nucleus in the potassium atom. Out of these, 2 electrons enter into the first orbit, 8 in the second orbit, and the remaining 9 electrons could not accommodate in the third shell. This is because the outermost orbit could only accommodate 8 electrons. So, 8 electrons enter into the third orbit, and the remaining 1 electron enters into the fourth orbit. Hence, the electronic configuration of potassium, K, is 2, 8, 8, 1. Similarly, let us see the electronic configuration of the elements like helium, neon, argon, krypton, xenon, and radon. Here, the outermost shells are having 8 electrons, except helium atom. Therefore, atoms which contain 8 electrons in their outermost shell can be considered to be chemically stable. Helium is also chemically stable, because the total number of electron in the helium atom is only 2, and so, it contains only one shell, and it can only be accommodated 2 electrons. The arrangement of 8 electrons in the outermost shell of atoms is called octet electronic configuration. Now, we look the electronic configuration of some of the other elements like magnesium, oxygen, sodium and chlorine. Magnesium has an atomic number 12. So, the electronic configuration is 2, 8, 2. The atomic number of oxygen is 8, and so the electronic configuration of oxygen is 2, 6. Likewise, sodium has 11 electrons, and chlorine has 17. So, the electronic configuration is 2, 8, 1, and 2, 8, 7, respectively. In this case, the electrons in the outermost shell are not having 8 electrons, and so these atoms are not stable. Is it possible an unstable atom to become a stable one? And if so, how it happens? For that we should study the chemical bonding. Chemical bonding. The atoms in a molecule are held together with an attractive force. The attractive force that holds the atom together in the formation of a molecule is called the chemical bonding. Through chemical bonding, atoms attain 8 electrons in their outermost shell, and thus gain stability by acquiring the lowest energy state. How do atoms of each element, which does not have stability, attain stability by acquiring the octet electronic configuration? Let us see some of the methods. One is ionic bonding, and another is covalent bonding. Ionic bonding. Ionic bonds are the bond where one atom gains electron, while another loses an electron. Let us look at sodium chloride as an example. Sodium atom loses 1 electron and form a sodium ion. The electron is not lost, but transferred to chlorine atom to form a chloride ion. So, we have a sodium ion and chloride ion. Let us analyze the electronic configuration of each atom. Sodium atom has 11 electrons and is distributed like this. 1 electron is in the outermost shell. Now look at the chlorine atom, in which we can see that it has a total of 17 electrons and distributed 7 electrons in the outermost shell. As we know, all atoms are always trying to become octet for the stable state. Here, the chlorine atom steals 1 atom from the outermost shell of sodium atom when they combine, and it fulfill octet electron configuration. The sodium atom loses the 3rd orbit and it becomes stable too. The interesting thing is, the number of electrons in each atom is completely changed after this process. Sodium atom now has 10 electrons, and the chlorine atom has 18 electrons. That is, sodium lose 1 electron, and chlorine gained 1 electron. Now, how these atoms actually stick together and become sodium chloride? Since the sodium atom has more protons than its electrons, it becomes positively charged. We know protons have a positive charge, and electron has a negative charge. In the case of chlorine atom, it is just opposite. Chlorine now has more negatively charged electrons that give it a negative charge. The positive charge of sodium is attracted to the negative charge of chlorine, like two oppositely charged magnets. That is, sodium is like a positive magnet, and chlorine is just like a negative magnet. So they bond together chemically. This is the way sodium and chlorine combines and forms sodium chloride. During the formation of sodium chloride, sodium atom donates an electron and gets converted to sodium ion, Na+. These positive ions are called cations. Chlorine accepts an electron to form chloride ion, Cl-. These negative ions are called anions. The oppositely charged ions, thus formed, are held together by electrostatic force of attraction. This attractive force is called ionic bond. Sodium chloride thus contains ionic bond. We can write the equation for the electron transfer during the formation of sodium chloride, as shown. Electron dot diagram. The transfer of electron between sodium and chlorine atom can be illustrated using an electron dot diagram. This represents only the electrons in the outermost shell, because they are the only electrons participating in chemical bonding. The method of representing electrons using dots around the symbol of an element was first introduced by the American chemist Gilbert N. Lewis. Let us see another compound called magnesium oxide. This is formed from magnesium and oxygen. Here 2 electrons are donated by magnesium atom, and 2 electrons are accepted by oxygen atom. Thus, they attain stability, and a compound is formed, namely, magnesium oxide. Let us see the dot diagram. Let us see another example, which is different from the above 2 situations. Elements of sodium and oxygen combine together and form sodium oxide. See the electron distribution of sodium and oxygen. Sodium has only 1 electron in the outer shell, while the oxygen has 6 electrons in the outer shell. If sodium atom donates 1 atom, oxygen cannot attain stability by accepting this 1 atom. Oxygen needs 1 more electron. Here it comes another sodium atom, and donates 1 electron to the oxygen atom. So, 2 sodium atom, and 1 oxygen atom needs to form the compound, sodium oxide. Compounds formed by ionic bonding are called ionic compounds. Covalent bonding is another type of bonding, and this is the bond between the atoms where electrons are shared. The chemical bond formed as a result of the sharing of electrons between the combining atoms is called the covalent bond. Let us take an example of fluorine molecule. Fluorine atom has 9 electrons and 7 in the outer shell, which is not stable. If another fluorine atom comes near to the first atom, see what happens. 1 electron is required for both the atoms to fulfill the octet, that is, to become stable. Here what happens is, a pair of electrons is shared between these 2 fluorine atoms, and they bond together. This is called covalent bonding. Now we can see that the outermost orbit is stable for both the atoms. So, it forms Flourine Molecule F2. Since one pair of electrons is shared in the formation of fluorine molecule. The bond is a single bond. A single bond is represented by a small line in between the symbols of the combining elements. Let us take an example of oxygen molecule. Oxygen atom has 6 electrons in the outer shell, which are not stable. It needs 2 more electrons to complete the octet. If another oxygen atom comes near to the first atom, 2 pair of electrons is shared between these 2 oxygen atoms, and they bond together. Since 2 pair of electrons is shared in the formation of oxygen molecule, the bond is called double bond. So, it forms oxygen molecule O2. If 3 pair of electrons is shared to form a covalent bond, then it is a triple bond. Nitrogen molecule is the suitable example for this. You might have understood that a fluorine molecule has a single bond, an oxygen molecule contains a double bond, and a nitrogen molecule contains a triple bond. It can be symbolized as F-F, O-O, and N-N, respectively. Let's examine how covalent bonds are formed when combining atoms which are different. For example, let us find the formation of a chemical bond in hydrogen chloride molecule. Hydrogen atom and chlorine atom combines and forms hydrogen chloride. Here, we can see 1 pair of atom is shared to form HCl. If a carbon atom is combined with 4 chlorine atom, 4 pairs of electrons are shared and form carbon tetrachloride. So, compounds formed by covalent bonding are called covalent compounds. Usually, covalent compounds are formed when non-metal combines. Electronegativity. The electron pairs shared in a covalent bond are attracted by both the combining atoms. In a covalent bond, the relative ability of each atom to attract the bonded pair of electrons towards itself is called electronegativity. For example, in the molecule of HCl pair, hydrogen is attracted more towards the chlorine. Thus, chlorine is more electronegative than hydrogen. Different type of electronegativity scales are proposed to compare the electronegativity of elements. Among these, the electronegativity scale, proposed by the American scientist Linus Pauling, is widely accepted. This is a relative scale with values from electronegativity of elements ranging from 0 to 4. Fluorine is the most electronegative element. Generally, if the difference in the electronegativity values of element in a compound is 1.7 or more, the compound generally shows ionic character. And if it is less than 1.7, the compound generally shows a covalent character. For example, in the compound carbon monoxide, the difference in electronegativity is 0.89, and so, it is the covalent nature. If we take sodium chloride, it is 2.23, and that compound shows the ionic character. Valency. Valency is the combining capacity of an element. It can be treated as the number of electrons lost, gained or shared by an atom during chemical combination. For example, elements like hydrogen, lithium and sodium atom, which contain one electron in the outermost shell. Therefore, they can lose one electron. So, the valency is 1. If atom contains less than 4 electrons in its outermost shell, the valency of an atom is equal to the number of electrons present in the valence shell. For example, aluminum has 3 electrons in its outermost shell. So the valency of aluminum is 3. On the other hand, if outer shell has more than 4 electrons, the valency is 8 minus the number of electrons in the outer shell. For example, chlorine atom has 7 electrons in the outermost shell. Here in this case, it is easier for choosing to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, which gives the valency of 1. From valency to chemical formula. See the chemical formula, a few compounds: sodium chloride, magnesium chloride, aluminum chloride and carbon tetrachloride. Let's examine the valency of each atom in the compounds and see the chemical formula. Watch sodium chloride. Here, the valency of each atom is 1. So, we can write the chemical formula of the compound sodium chloride as Na1Cl1. NaCl. How would you write this formula? See the rules. First, write the element with lower electronegativity. Exchange the valency of each element and write a suffix. Divide the suffix with the common factor. If the suffix is 1, it need not be written. Let us write the chemical formula of aluminum chloride. Aluminum has less electronegativity, so it is written Al initially. Then write chlorine, Cl. Aluminum has a valency of 3, and chlorine has 1. Now, exchange it, and write a suffix to each atom, as Al1, Cl3. The suffix need not be written. So, the chemical formula of aluminum chloride is Al, Cl3. Now, watch some of the chemical formula for the compounds, such as magnesium oxide, carbon tetrachloride, carbon dioxide. Oxidation and reduction. Oxidation is the process of donation of electrons, and reduction is the process of accepting electrons. Let us see the magnesium chloride formation. Magnesium has an electronic configuration of 2, 8, 2, and chlorine has 2, 8, 7. While combining these, magnesium atom donates 2 electrons to 2 chlorine atoms each. In this process, magnesium reduces chlorine atom by donating electrons to it. Therefore, magnesium is considered as the reducing agent in this process. Since chlorine oxidizes magnesium by accepting electrons, it is considered as the oxidizing agent. Oxidation number. Oxidation number is the number indicating the oxidation state of an element in a compound. In ionic compounds, The oxidation number is the number of units of charge gained by the atom after bond formation. If an atom is gained N after bond formation, then it must be negative number. If it lose electron, it must be positive number. For example, in a hydrogen chloride molecule, chlorine acquires a negative charge by accepting one electron, and hydrogen acquires a positive charge by losing an electron. So, the oxidation number of chlorine is -1 and +1 for hydrogen. We can say oxidation and reduction in terms of oxidation number. The process in which the oxidation number increases is called oxidation, and the process in which the oxidation number decreases is called reduction. As oxidation and reduction take place simultaneously, the overall process is known as a redox process. The molecule, which contains the atom, whose oxidation number decreases during the process is called the oxidizing agent, and that in which oxidation number of an atom increases is the reducing agent. See the reaction with carbon and chlorine. Here, chlorine is the oxidizing agent, and carbon is the reducing agent. Because the oxidation number of chlorine decreases from 0 to -1, and the oxidation number of carbon increases from 0 to +4. Let us see another reaction of zinc with hydrochloric acid. Here hydrogen is the oxidizing agent, and the zinc is the reducing agent. The oxidation number of hydrogen decreases from 1 to 0, and the oxidation number of zinc increases from 0 to +2. The oxidation number of chlorine neither increases or decreases.